Inviting someone like Luciano Paz on a stats podcast is both a pleasure and a challenge. He does so many things brilliantly that you have too many questions to ask him. In this episode, I've chosen, not without difficulty, to focus on the applications of Bayesian stats in the marketing industry, especially media mix models, aka MMs. Well, okay, I also asked Luciano about other topics, but you know me, I kind of like to talk. Originally, Luciano studied physics, and then he did a PhD and postdoc in neuroscience before transitioning into industry. During his time in academia, he used stats, machine learning, and data science concepts here and there, but not in a very organized way. But at the end of his postdoc, he got into PyMC, and that's when everything changed. He loved the community and decided to hop on board to exit academia into a better life. After leaving academia, he worked at a company that wanted to do data science, but that for privacy reasons didn't have a lot of data. And now, Luciano is one of the folks working full-time at the PyMC Labs consultancy. And Luciano is not only one of the cool nerds building this crazy Bayesian adventure, he also did a lot of piano and ninjutsu. So don't provoke him, either in the street or at a karaoke bar. This is Learning Bayesian Statistics, episode 63, recorded May 19, 2022. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Pandora, like the country. For any info about the podcast, learnbayestats.com is la place to be. Show notes, becoming a corporate sponsor, supporting LBS on Patreon, unlocking Bayesian merch, everything is in there. That's learnbayestats.com. If with all that info, a Bayesian model is still resisting you, or if you find my voice especially smooth and want me to come and teach Bayesian stats in your company, then reach out at alex.andorra@pymc-labs.io or book a call with me at learnbayestats.com. Thanks a lot, folks, and best Bayesian wishes to you all.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations.
What's a Bayesian? It's someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men, dropping placebo-controlled science like I'm Richard Feynman?
Hello, my dear Bayesians. I have two great news for you. First, as usual, I want to welcome my brand new patrons of the show, especially those in the full posterior tier or higher. This time, I'm talking about the unique Lin Yusha and Omri Har Shemesh. Your support is invaluable, and I am so grateful for it. Second, with my friends and fellow PyMC core developers Thomas Vicky and Ravin Kumar, we've just released our first online course. We made this intuitive introduction to Bayesian stats for the quick learners, the action takers, and the busy professionals who've always wanted a one-stop shop to learn about the modern Bayes revolution. You will get a lot of code examples and practical applications, not math equations, and you will integrate a community of like-minded learners online because we are all in this together. Course registration is open for the next week, and we'll close them afterwards to focus on what we do best, which is helping the first cohort settle in and absorbing all this new material. If that sounds interesting to you, then go to intuitivebayes.com and check out the syllabus, as well as 2 full lessons that are available to view for free for a limited time. That's intuitivebayes.com. And now, let's talk MMMs and eat M&Ms with Luciano Paz. Luciano Paz, bienvenido a Learning Bayesian Statistics.
Thank you, Alex. Thanks for having me.
Actually, I should say Learning Bayesian Statistics, actually.
Estadística Bayesiana.
Estadística Bayesiana.
How I discovered Bayesian stats like that.
Yeah? Oh, okay. When I was in Argentina, I was telling people I was doing that. And first they told me Bayesian. And the first time I was like, is that the same thing? And then I understood, oh, that's the accent. Yeah, of course. Yeah. So let's start with your origin story, actually. How did you come to the stats and data worlds?
So it's kind of a long story. I started studying physics.
Okay, we have 3 hours.
That's enough.
Okay.
Let's make it short. I studied at grad school physics. In Argentina, it's called licenciatura. So I don't know grad school, actually, if it matches, but no matter. So I studied physics, and at one point, some genius decided not to teach probability or statistics in physics. So all of nor any sort of programming, and make all of those optional. And so you would just run into problems. You had some courses like they were practical laboratories where you had to go and measure things. And then suddenly you had data and you have to do something with the data. And they kind of taught you some patchwork to do on that. And I said, this is horrible. So there has to be something better. and luckily, there was some courses that were not mandatory that you could do. And there was this super professor in physics. He was involved in this Large Hadron Collider experiment.
Oh, okay.
Yeah. And Ricardo Piegaya. So this guy taught an excellent course on probability and statistics. And basically, everything that I learned from probability, I learned it from him. And at some point, it was really from the ground up, like what's probability, what does stats mean, and naturally you go into the frequentist world. And then suddenly he said, yeah, well, but there's also this other point of view that's Bayes. And he motivated it by, as he worked for the Large Hadron Collider, he motivated it with a physics experiment that there was some data that they wanted to measure the mass of some particle. Now I forgot everything because after grad school, I didn't work in physics anymore. So they wanted to measure the mass of some particle, and the way in which they measure these with really weird, exotic materials is that they somehow see some traces, and you have some really noisy curves, and they try to do a fit of the noisy curve and see where this curve passes through an origin point of something in a coordinate system. And due to the noise, this line that they were fitting was going into negative masses. And so theoretical physicists love to think of crazy ideas and say, how can we explain negative masses? No, it has to be an imaginary particle that does blah, blah, blah. And then someone said, maybe it's just the noise, right? So maybe if we set a prior that says that negative masses are impossible, we might learn some valid mass. And so they came up and started to use Bayes by just saying masses can't be negative, they have to be positive. And just with the noise, they managed to estimate a proper mass that was positive and was valid with the noise that they were getting in the experiment. And so he taught it like this. There were some reasons, there were some pros, that you could explain these sorts of results that the other framework was completely ill-suited and spurred people down completely wrong avenues for future research, like people saying, let's explain negative masses. And so that was kind of the thing that I saw in physics. Then after grad school, I started to PhD in neuroscience. And again, like having almost no background in programming, and little background on probability. Neuroscience is mostly you have to program stuff and then you have to collect data and analyze the data with stats and anything. So it was like a patchwork again with artificial intelligence methods that I was learning on the fly, machine learning methods that I was learning on the fly, and always feeling ill-equipped and underprepared for everything. So it was a quite strange experience, the PhD, that I was exposed to many, many different things. Like I had to go to courses with programmers. I had to go to study some things that I had never seen before regarding like databases and compilers and things like that. And then during my postdoc, I continued with neuroscience, but now I wanted to go a bit more back to the origins with physics and everything. And well, my boss at that time was not interested on that avenue. And he said, let's try to do this instead. And doing that, I said, well, yeah, the methods that you're using are all horrible because they give you really bad results. You should switch to Bayes. And so I started to try to spur them into Bayes. And at some point, I remember that I was really excited that I was going to analyze neural data. Like you have these electrodes in brains of animals, and then you get a set of spike trains, which are like these events that you see, that the neuron bursts into activity and then becomes silent. I really wanted to model those kinds of data sets. But for some reasons, the lab was never shared these things with me because someone was already working on those. So I was always caught with behavioral studies and the high-level data overview things that I always did. And when I said, yeah, let's work with this spike train data, I started to read how to decode these spike trains. I found the super paper that I said, this is awesome, where they use Bayesian methods to try to do model comparison on the spike trains. So briefly, I was working on something called decision making, and there was some experiments on mice and rats and monkeys suggesting some area of the brain did some really particular way of dynamics to lead to the choice of the animal. And what people used to do was that they record the animal doing a task that the animal had to make a decision many times. And they had many spike trains, each for every trial. And the spike trains were really noisy, so you couldn't see any pattern in these. So they would just grab all of them, align them to the start of the experiment, and then average them. And when you average them, you saw like a really smooth or kind of Gaussian random walkish excursion of the average firing rate of this population of neurons. And when it reached a really fixed level of firing rate, the animal would decide. And so they said this is evidence that the brain is working as something called the drift diffusion model. And then someone came along and said, maybe you're wrong, and the brain doesn't do, like that area of the brain doesn't do exactly that, like averaging. Maybe it does something more binary. And what you see is that the time in which you make the jump to a decision is different for each trial or for different neurons. And then when you average across all of these, you get this sort of smooth thing. And so they did this Bayesian model fitting single trial neural data and then a model comparison with the drift diffusion model. And they said, yeah, most of the neurons work as this sort of binary outcome that they have low firing rate, and then at some point, some latent feature says, I've decided in favor of option A, and they jumped into high activity. And when they did all of this, they just realigned the data, like the raw data, to this sort of inferred point of the switch. And like it was magic. Apparently, like all of the noise completely disappeared. You saw all of the binary activity of the neurons. Like you could see all of them aligning perfectly to this switch point and then having low activity and high activity. And I said, this is awesome. And I wanted to try to do something like that. Regretfully, it was in MATLAB, and they were doing things with CUDA. And I said, oh, there has to be something out there that does that I could use to do something similar to this. So I naively Googled Python, Markov chain, Monte Carlo, and that's how I learned about PyMC. And started to see, what can I do with this? And got involved. In the end, I finished my postdoc and left academia before I actually did anything of neural coding with Bayes. But it gave me enough time to get involved with Bayes and with PyMC, enough to really like the community, really like what you could do, and say, I want to just switch to working on machine learning stuff or Bayesian stat stuff more than what I was doing with neuroscience. So that was my weird transition from physics to, well, not to neuroscience, physics, neuroscience, then to do stats and stuff.
Yeah, that's a very sinuous path. I like that. And my first question is, how did the first switch happen? Like, why did you start a PhD in neuroscience when you just were doing a grad degree in physics? How did that happen?
Well, I've always been fascinated by the brain, and there was, in the physics department, there were some people that were working in neuroscience. So it was technically, I never left physics.
I see.
But practically, I was always working with neuroscience and not doing anything related to what I had done during grad school. The only things related were, well, stats in the end.
I see. Okay. Because I was like, that's interesting. And then discovery of PyMC was kind of random, right?
Yes. So, and compared with Stan and with Bugs and with Edward at the time. And like I made the decision to go with PyMC based on a few blog posts that I read on what they were the features of each, and said, yeah, let's go with PyMC.
Were you already coding in Python at the time?
Yeah, I was coding in Python at the time. I had learned my very first programming language that they taught me in high school was Pascal.
Oh, you too?
Yeah.
I learned that too in high school. I hated it.
I don't really remember. Like, I've deleted most of the things that happened to me in high school. I remember that they taught me this, but I could not do anything in Pascal now.
Yeah.
And then at one point, again, in physics and in these laboratories during grad school, that they said, yeah, you have this data, try to analyze it. We were using some software thing that worked like Excel, and you had some hard-coded methods inside. And at some point, if you wanted to do anything that was outside of the things that were already coded, yeah, good luck, you couldn't do anything. So we said, no, I want to try to learn how to do something. We were doing something with lasers, I don't remember at the time. And we wanted to program something related to the information that we were gaining from the lasers. And so that's how I then approached my second programming language, which was MATLAB, because people said, yeah, you can't code that in this Excel-ish like thing. You have to go to another thing, and we have MATLAB installed, so try MATLAB. And so I went to MATLAB, and I coded horribly until I went to a course with some people from computer science, and they looked at what I coded and they said, that's horrible. Burn it. Burn it with fire.
Stop that right now.
No, stop doing that. No, that you don't program like that. How can you read that? And they made a challenge to me, like, try to go and read the code that you wrote a year ago and tell me what it does. And I tried to do that, and I couldn't. It was, okay, you're right. I'll change, teach me. And so that's how I switched to Python and to better coding standards.
Yeah, I see. Yeah, basically in your path, there's a lot of, you were interested in something and you just you stopped doing the thing you were doing before and then switched to that new thing that you were more interested in, and then learned what you had to learn on the fly. Find that very interesting, and I think that's quite inspiring for our listeners if they are considering going into Bayesian stats. Like, it's definitely doable, even if you don't come from a classic stats background.
Yeah, you can self-teach, but it's lonely and hard to do the self-teaching part. But in the end, I'm much happier now.
Yeah, exactly. Yeah. I'm wondering though, if at the time when you took those decisions to switch, like how anxious did that feel to you, or were you actually happy to go into those new territories?
So these sorts of natural switches from the classical physics settings and things to neuroscience was supernatural for me and no anxiety whatsoever. But then at some point, as I advanced in my academic career, I started to feel that academia was a horrible place to work in. I had left Argentina. I was in Italy and with kids, and it was really difficult to continue the academic life without switching countries. And so I had to try to find a new version of me, or something in which I could work and change, but leave academia. And so I made a conscious decision to go out of neuroscience and physics, like my background, and try to convert myself into more industrial data scientist. And I was planning on exploiting the things that I had learned from stats and Bayes to try to do that. And so that switch was really awful, full of anxiety, depression, and then also uncertainty. Like, what it's like, yeah, I'm not alone, and I find myself jobless. How can I support my family and whatnot? Luckily, I managed to go into a first company that hired me. They were really interested in employing machine learning and artificial intelligence, but just because it was trendy and sounded cool. They were working in some security businesses, and so they wanted to provide the clients with some automatic interpretation of data that they had. And the problem when you have these sorts of systems and these sorts of things is that the company does not have access to the data of any client due to privacy reasons and also legal important reasons. So it was you want me to build some sort of automatic system based on no data. And I have no idea how to do this. So let's try to find out. And so it was a weird switch because I came from research and I just went into research, but on a different topic at this company. It was kind of disappointing because I was expecting to find a bigger team inside of there to work with. And I was basically alone because it was the company's business core was in a different sector. And there were classical C, C++ developers and people working in Java because they were interfacing with some chips that this company was building. And so things that were really more low level. And then there was me saying, let's see if I can do machine learning on some data or some imaginary sort of data that I was inventing and seeing. And in the end, I learned a lot thanks to that. But it wasn't my dream job. So at some point, Thomas Vicky, who I knew from PyMC, came and said, I'm planning on starting up a consultancy. And I said, I'm in. Totally. But I need some reassurances that this thing works, this company can work, before I actually commit to quitting my job here in Italy. And so I saw how the thing was evolving at the beginning. And then when I saw that this was working well, I made the switch and never looked back.
Yeah, so perfect. You anticipated my next question, which was like, but what are you doing today? And so now actually we are colleagues.
We're colleagues, Alex.
Yeah, like I remember, I think you told someone that you thought like your colleagues were the smartest you've ever worked with. I really appreciate that.
Oh, that's definitely true, Alex.
No, that's cool. And I remember we joined Labs full-time, I think the same day or something like that.
Similar, yeah. It was weird.
Yeah, we both like quit our current job and like then joined full-time. That was cool. And since then, a cool adventure started. And so actually, I'd like to talk a bit about what you're doing at Labs. But maybe first tell us how you started contributing to PyMC. Because you told us how you discovered PyMC and then you were using on that research stuff. But how did you start contributing to the package?
Oh, that was also kind of fun because when I discovered PyMC, I said, okay, so let's try to use this thing. So I went to the start. There was this quick start on what you had to do. And it was like, you have this normally distributed data. Let's infer the mean and the standard deviation. And you do pm.sample, you infer it, perfect. And I was like, okay, everything worked, but I have no idea what's happening. So what's this new variable that I'm creating in a model? And so I would start to try to say, okay, so let's give me some data, mu. And it wouldn't give me any data. And I had no idea if the model that I was building was doing what I wanted it to do. And so I started to look into the source code to try to understand what was happening under the hood. And I kind of learned that there was this random method that you could call on some variables and they would give you draws from the variable. And so that's how I started to try to see if what I was programming when I was learning was working. And quickly I discovered that you couldn't do this with everything. There were some values that you just couldn't call random on. And so you had to do this sort of switch. Sometimes you said, I'll call random. Sometimes I'll say eval. Sometimes I would just say something different, like get value or value. And I felt that all of this was unpleasant. And I wanted to have a method to be able to say, I wrote a model. I have no idea if the model was the thing that I had in mind. And the only way that I learned how to say if the model is correct is if you give me values, like candidate values of these, and I plot them and I look at them and I see if they're okay with what I had in mind or not. And so basically that's how I went into PyMC and I said, okay, I want this feature and it's not working for me. So I kind of developed in some really long iterations the forward sampling for prior predictives. There was also some stuff done by Colin Carroll that at that time where he restructured part of the code in between two things that I did. And so eventually I kind of entered PyMC and contributed it while I was still learning PyMC, saying, this is so hard for me to learn if I can't draw samples from these. So I kind of learned that piece of the library because the library was huge. I had no idea what was going on with the samplings, the step methods, the Hamiltonian Monte Carlo. I was just to the dumbest thing of drawing prior predictive samples of a model. And slowly, that's how I started to learn PyMC. And so how I started to get involved with all of PyMC and said, oh, this is super nice. And the community was super welcoming. And everyone said, yeah, this is great, awesome work. So let's try to do this. And eventually they invited me onto the developer chats and developer meetings. And while I was in my academic life, again, as I said, I was mostly always alone doing the academic life because colleagues were doing other things, and I was like the only stats guy or programming guy or the only whatever guy in the group. And so having these sorts of, well, not peers, all of them were senior to me in PyMC, say, yeah, come aboard and let's discuss together the future of the package. It was like incredible for me, and I really loved it. Eventually, the thing that I needed at the time was something related to mixtures, because of the data that I was working with. Like the recordings were a bunch of neurons, and you didn't know there are different types of neurons in the brain, and different types of neurons also respond differently to signals. And then maybe you have the same type of neuron, but some of them have some virus that was injected to make them responsive to some like light signal that you have. It's called optogenetics. And you have other sorts of like really diversity across a single piece, a single like square millimeter of brain tissue. And when you record, you don't really know what you're getting. And so a priori you have like a mixture distribution on everything that you could have. And I wanted to model with mixtures and found that you couldn't do everything that I needed with mixtures at the time. So I kind of tortured the mixture class into giving me what I wanted. In the process, I made it a bit of a mess because I was learning while I was doing it. And now it's much better thanks to the transition into V4. Everything that we learned and the awesome work also by Ricardo and many, many others, like the mixtures distributions are now much nicer. Like I feel that all of the package is evolving in a much better direction than where it was in version 3.
Yeah, the version 4 of the package is like really, really amazing on a lot of dimensions. And I'll get Ricardo Vieira very soon on the podcast, where we're going to dive deep into the novelties of PyMC 4.0 and how much better that will be for users and how that came up. But okay, super interesting. Basically, like you took the opportunity of having to work on a mixture model to both learn about mixture models and learn about PyMC, and that's basically how you became a core developer and integrated the team.
Yeah, and patched PyMC in the process while I was learning. So imagine how dangerous that is, and the trust of the community also in doing this.
Yeah, no, but I mean I guess that's what a lot of us do, right? It's also how I ended up in the core team, right? It's like contributing stuff that I was learning on at the time and that were also useful to the package, and that way everybody benefited because the package needed those improvements. You needed to work on that because you were interested in that. So that's super cool. And so surely I have too many questions for you, but let me select the most important ones. Actually, since we're talking about them, can you actually talk a bit about mixture models? Because we did talk a bit already about that on the podcast, but not really formally. So can you tell listeners what mixture models are and when they are useful?
Yeah, well, the basic idea is when you have Bayesian hierarchical models, you sometimes know that there's some categories your data belongs to. And these categories are quantitatively different between each other because maybe there's a parameter that's different across categories. Like in the classical radon example, you have the baseline radon measurements for different counties in the dataset. And if you know to which county you have the recording, then you can exploit more information. So imagine this sort of same dataset, but if you don't know the label of which county these recordings came from, it's kind of a mess because you have things that seem to be multimodal inside of the dataset because you know that there's some groups in them, but you don't know the labels of each of the groups. You don't know each observation that you got to which group it belonged to. So somehow you have to try to, at the same time that you're learning properties of these underlying groups, you have to learn the labels of each observation to the group. So trying to do that is really difficult because these labels, if you imagine that you have a finite mixture, so these numbers of groups are limited, I don't know, maybe 10 groups, each of the observations can belong to one out of these 10 groups. So this is a discrete variable. And trying to do inference on the properties of each of the groups and also on what value this discrete random variable for each observation should take is really hard, because you can't do Hamiltonian Monte Carlo. You need to do something like a block step method where you do some metropolis steps on these discrete random variables, and then some sort of Hamiltonian Monte Carlo, if you can, on the continuous variables for each of the groups. So trying to do at the same time the label of each of the observations and the properties of the groups is really difficult. So what some people do is that they say, I won't try to learn the explicit label. I just want to learn the group properties out of this. And so the way in which they do this is they sort of marginalize out the labels. So basically they say, maybe I belong to label 1 with some probability, I belong to label 2 with some probability, label 3 with some probability, and then my observations will be what would have been observed for label 1 times the probability of having belonged to label 1 plus what I would have been seen from label 2 times the probability of belonging in label 2, and so on and so forth. So you basically kind of sum all of these labels together, weighted by the probability that you can also try to estimate of each observation belonging to each of these labels. So you bypass the problem of labeling the data to each of the groups and directly say, what's my group level values? So these groups that you actually want to infer, what the values are. So that's like the classical way in which mixtures are introduced, because you know that there's some labels inside and you know that they have a meaning. But then mixtures can also be like a tool to try to model complicated distributions where you don't know if they're the groups inside of them, but you know that the distribution looks kind of weird. And this was a problem that we had in some marketing field for retention data. Like people watched the video and you had to learn the retention, how much of the video they watched. So basically what you do is you can say, I will assume that my observations come from some sort of mixture distribution. Each of the groups of this mixture have absolutely no meaning. Like they don't have any physical interpretation. But what does have a physical interpretation is this sort of marginalized value. So it's sort of a tool to model complicated multimodal distributions that you say they can't take the form of a Gaussian or exponential family or other sorts of distributions. So you kind of build them by combining simpler pieces and weighting these simpler pieces. Like the typical example of this is when you do KDE plots, kernel density estimates plots, you basically are doing a mixture model because you show some distribution, like a smooth distribution, which is basically the sum of many Gaussians, and they're weighted by some weights that are in the method of the KDE. So that would be like the more data-driven way. And then there's these crazy things that you can do, like Bayesian non-parametrics. You go into the realm of things called Dirichlet processes, which you try to learn probability distributions again, like these sort of complicated entities. So mixtures are really deep, but they're plagued with complicated problems.
Yeah, and especially since so you said that if you want to learn the labels, right, you have to infer integer values, right? Because it's like this cluster is cluster 0, this one is 1, this one is 2, blah, blah, blah. And so you have to infer that, and so you cannot use HMC for the whole model. Yeah. And so that's why often people will marginalize out these labeling to be able to use HMC. So you gain that. What you lose is you cannot label the clusters anymore. So what does that mean? It's that you're not able to say that data point belongs to that particular cluster.
Yeah, exactly.
Yeah, you cannot say that anymore. You can just say, I have clusters and each data point belongs to one of those clusters, but I cannot tell you which cluster it belongs to.
Yeah, but you don't learn that in the model, in the inference run. We did have a project with labs, like the very first project that I worked on, that they disliked the idea of losing this information. They wanted to be able to learn this. So you can with some really, you basically have to do Bayes rules by hand, and it only works if you have a finite mixture. So you assume that there's some finite group length, and you can then apply Bayes rule by hand to try to extend what you learn from the marginal distribution, like this sort of marginalized out the latent labels. You learn the posterior distribution, which is marginal because you don't have the label information. So you can afterwards extend this marginal posterior to include, with Bayes rule, the labels and the probability of each of the labels being like for each of the observations. But yeah, so this is something that is doable, but it's only doable when you have finite mixtures, like they're not infinite mixtures or continuous mixtures.
Yeah, it's tricky.
It's really tricky to do.
Yeah. Okay. So basically mixtures can be very powerful, but they are hard to work with.
Yeah, totally. And also going back into this Dirichlet process and the marketing of retention, we weren't interested in trying to give a meaning to each of the clusters that were modeling. We were interested in trying to learn the entire probability distribution or model the probability distribution.
So the probability distribution you're talking about here is the probability of each data point to belong to each cluster?
No, this is more abstract. It's like you have someone that watched an advertisement and they watch it through some percentage of the ad. And then you have a distribution, like you repeat this with 100 people, and then you have many observed retentions of the video. So you have many percentages of the videos that were watched. And so this gives you a weird shape distribution because maybe there's some points in the video that are really important for the marketer. Like they want to see the ad, they want to see the brand, for example, or they want to see the message of the brand, or they want to see the promotion code. And what's the probability that the person actually arrived to these key moments? So there's some dynamic models that you can try to learn. You can try to model the history, like kind of the dynamic of the viewer, if the viewer was engaged and then went out, or you can take a different approach, which was what we did, which was to try to say, let's try to learn from these observations, the probability distribution of retention, and then compute the marginals or the stats of how many, or what's the likelihood, what's the probability that you'll have arrived to these key landmarks of the ad, seeing the brand, seeing the promotional code, things like that. So how likely is it that the viewer arrived to this? And that then gives you a measure of the ad's effectiveness, and you could compare. That was basically the task, try to see which ad was more effective.
And so how is that related to Dirichlet processes?
So the distribution of retention was not unimodal. You had multimodality and you had bumps in it. So it looked like a mess because there were people that would drop off as soon as they could. Some people would watch the full video. Some people would watch it halfway and then drop. And this wasn't smooth at all. It was a mess. And so how can you model a mess and then extract some summary informations from this? So that's how what we did was establish a Dirichlet process prior on this. Actually, a hierarchical Dirichlet process prior on this, where you try to learn the full probability distribution of retention out of this. And so it's kind of like you grab the data, and instead of doing a naive KDE or histogram of the data, you do something a bit more sophisticated, and then you can compute these summaries on the data that are really relevant for the marketer.
I see.
Which if you try to do with the raw data, you get noisy estimates and anything.
So it's like a bit of generalization of the mixture models, right?
Yeah, it's sort of mixture model.
Instead of having a finite number of clusters, you are also inferring the number of clusters with the Dirichlet process.
Yeah, the Dirichlet process is something that in principle you have infinite number of clusters. But in practice, you have fewer because the probability that you'll arrive to a huge number of clusters decays.
But it's like here, you didn't know exactly the clusters, so you used the Dirichlet processes to discover those clusters.
Yeah, kind of, yes. But the complicated thing with this is that with mixtures, with any kind of mixtures, you can have problems that are called label switching. So you can infer some parameters for each of the clusters, but if you change the labels of the clusters, like cluster A and B, now you call them B and A respectively, this is exactly the same because they bear no meaning. Just the sum of these, the weighted sum, bears a meaning. So this sort of label switching made sampling hard because the chains would not converge to the same values. You would have different chains converging to different values. But like if you looked at most of the chains, the different chains in the runs, like some clusters would have been labeled with labels A and B, and in a different chains they were labeled as B and A. So it was this called a label switching between the properties of the cluster. And you couldn't really fix that beforehand. There are some techniques that we knew worked with unidimensional cluster parameters, but this was multidimensional. So we kind of had to go in and work with post-processing, like trying to fix the label switching problems. But that's one of the most complicated things in mixture modeling, is this probability that you'll switch from labels and maybe your distribution will be multimodal afterwards. Like the posterior might be multimodal because of this label switching. And so that's why they're not so much used in practice.
Yeah, Dirichlet processes are really hard. We could continue on that, but I want to ask you also about MMMs. So maybe do you have some resources that would be interesting for listeners who are interested in Dirichlet processes and mixture models that we could put in the show notes?
Oh.
No problem. If you don't, it's okay. Like, I think there are some examples on the PyMC website. I'll link to those.
Yeah, and also some really nice some really nice case study written by Michael Betancourt, which explores this sort of label switching problem, and he called it the mixture degeneration problem. Jumpeng Glau also translated the code into PyMC from that case study, so I can look that up.
And that's about mixtures, right?
Yeah, those are mixtures, traditional mixtures, but the problem is for every mixture.
Yeah.
You have the same exact problem. Then Dirichlet processes, I've read it through different places, and I've always found the explanation to be incredibly unsatisfying, because they come and they shoot you with, personally, the most horrible line of math that I've seen. And they say, yeah, but rest assured, this isn't so hard. This is like a Bayesian histogram, and feeling that actually helps you. They think that line is something that might say, oh, right, a Bayesian histogram. And like, what's that? No, I don't know. I've read it in Bayesian data analysis from Gelman. Also from Osvaldo's book, it's nice because it goes into like a more simpler explanation of mixtures, I feel. But like in practice, as I've mostly done, I've covered things by looking at some papers, some books, and not so... I couldn't recommend one reference. I don't really know.
And so Osvaldo's book, which one do you mean? Bayesian analysis with Python?
The first one, yeah.
Yeah, I'll put a link to it in the show notes. I'll also put a link to the references you talked about, so Betancourt's case study. And if you have Junpeng's port of that code, that'd be great to add it to the show notes. And also on episode 4, so very, very beginning of the podcast, I had Karen Knudsen here, who works a lot with Dirichlet processes for neurodegenerative diseases, and I had her on the podcast to explain exactly what a Dirichlet process is. So hopefully, with all that information, people will understand a bit better if they are interested in it. If you don't worry, it's normal. Like me, I'm like exposed to those things regularly, and yet each time I have to think about it again. I'm like, wait, what are Dirichlet processes again? What are they used for? So it's like, I feel like you need to do a lot of Dirichlet processes model to develop an intuition of what they are and when they are wrong. Okay, so now, actually, let's focus on, you talked already like about application basically of Bayes in marketing, and you talked about that attribution model in a way where a hierarchical Dirichlet process, which is like even more complicated. It's like mixtures are hard, Dirichlet processes are harder, and then hierarchical Dirichlet process is incredibly hard.
Actually, I found it to be it was exactly almost the same as Dirichlet processes. And that was surprising for me. I can find that reference. That one I do have the reference where I found that you could reparameterize the hierarchical Dirichlet process to have it as a Dirichlet process with just one parameter that was changing through elements of the hierarchy.
Well, perfect. Yeah. If you can put that reference in the show notes, that'd be perfect. I'm sure listeners will love that. And so another thing that you worked on a lot for marketing data, actually, and that was also with labs, and that was pretty interesting projects, and I was part of some of those. And these are basically media mix models. So can you first give us a high-level answer of why media mix models, and especially with the Bayesian framework, would be helpful in marketing?
So media mix models, they try to answer a key question, or try to help answer a key question in marketing, which is how you should distribute your marketing budget. So basically, there are many places where a company can place ads. They can place them in YouTube, they can place them in Facebook, they can spend money on search engines to get them to show their website at the beginning, they can spend their money on TV ads, on radio ads, having influencers talk about their brand or whatever. So there are many things there, and each of these channels from marketing might bring you a customer, and that customer might see the website and then say, yeah, or whatever it is that you're trying to sell, and yeah, I'll buy. So the key thing after you spend some money on these different media channels is to try to infer, well, where should I put more money to increase sales? Or where can I put less money and don't have my sales be so affected by decreasing that? And there were some key challenges. I've read some studies that of some companies where they collected data through cookies, and they were spending quite a lot of money on some providers through these, and they were saying, yeah, I've gotten so much thanks to the cookie. I don't remember how this went, but there was some attribution to which of the providers had brought in the customer. And so they were paying to these providers something. And at some point they said, let's try not to pay them anything and see what happens to our flow of customers. And they saw that their flow of customers, it didn't change at all. So it's like this provider, which was being imputed through cookies, was like a ripoff. And so essentially, companies, to be able to perform well, they have to do these periodic experiments where they try to do lift studies or different types of experiments where they see, I have a really controlled group of audience to which I show in one channel my advertisements, and then to another I don't show, and then I see what happens to the overall probability of seeing conversions or not. And so I can assume, or I can infer how efficient the media channel is. So you have all of these marketing techniques which give you these sparse observations. Media mix models essentially try to come in and reconcile these sparse interventions, which are sometimes called lift studies, with what you actually see every day, which is the total number of customers and how much you've actually spent on every channel. So they come in and tell you, media mix models try to learn how many customers came through each advertisement channel. And they do this with some sets of priors on the types of dynamics of advertisement. So one of the things that they assume is, if you don't spend any money on a certain channel, the channel will bring you anyone. Like people will just come from other channels there will be potentially some natural flow of customers, which might have a time modulating effect, some seasonality components or some other properties in this, but people won't be coming through this advertisement channel. So if you spend 0, you get 0. But if you spend a lot of money and you double that afterwards, maybe you don't get double the clients or double the customers. So it's like you hit some roof after you've spent a certain amount. So this is called like a saturation effect. And then you also have something like if you spend some money in a given week, maybe a person has seen the ad, has become aware of the brand during this week, doesn't decide to do a purchase in the week that he saw the ad, but decides to do it 2 weeks afterwards. So you have this sort of leak effect where the effectiveness of a channel might spread through time. So this is called like sort of ad stock transformation, where you give some money to a channel and the total number of people or customers or conversions or whatever your business needs are increases, but not only on the moment that you show the ad, but some time into the future. So taking into account these kind of basic marketing assumptions on the process, they try to estimate what, after you've spent $1 million on marketing distributed between 20 different media channels and you got, 10,000 conversions, where did your conversions come from in the media channels? And how could you optimize the budget afterwards? So that's how media mix models come into play.
Yes, thanks for this overview. And I mean, these models are, it seems simple, right? Like this, the question it tries to answer is like apparently trivial. Right? It's like, I spend that much on Google, tell me how many customers I got from Google. But it's actually very hard. And there is a lot of unidentifiability and things like that. And the models in the end that you ended up contributing to for that project is huge. And I mean, maybe can you tell us the main difficulties that you encountered with this project and the model and how you, like, what you learned from all this?
Yeah, so main difficulty, as you said, is this unidentifiability, which I think isn't just for media mix models. This is deeper into some linear regressions. The problem is that you only see like the total number of customers. You don't know the origin of each of the customers. So you have one value, that's the outcome, and you know that it could have come through 20 different ad channels and also potentially people that just come in naturally. So from, like, you call them from the background. They don't come through the ad process, they come through other different natural processes. So these come from the background. So having these 21 sources to just one single output is really difficult to try to disentangle the contributions of each of the ad channels. What makes it even more challenging is that the spend on different channels is correlated. So you have, it's also natural, maybe the company grew, and so the spend across every channel grows. And maybe the company foresees some difficulties in advance and has to reduce the budget in advertisement, and it reduces it uniformly through every channel or proportionally to the spend. Like drop 10% on every ad channel spend. So like they aren't completely correlated, but they're quite correlated every different ad channel just to how things work. So imputing to which channel each of the customers came from is a really difficult task. And at the core of this, after you've imputed this, you can then see how efficient the channel was. So how much money you have to pay for a given marketing channel to get one person to come in. So this is called cost of acquiring a customer, CAC. And so one of these measures of efficiency of a channel is the CAC of the channel, the cost to acquire a customer. And so that's a key difficulty. The only thing that can truly disentangle these are these controlled interventions, which are called lift tests, that can't be performed every time, like really constantly. They cost a lot of money to do. You actually do a whole intervention, maybe geographically located in some place, where you say half of the people that will be in some target audience will be exposed to my advertisement in one particular channel and half won't. So then we see what happens to the conversions that you see afterwards. And these experiments are really difficult because they depend so much on the properties of the channel. So for example, how do you do this with TV? It's like you can't do this at a fine level of within a city target an audience. You have to say, well, maybe a district I'll show the ad, another district I don't. So these are like geo-located separations, and maybe there will be a confounding between the geographies that also affects how likely someone will have converted into this. So these experiments are costly and they're difficult to do. You can't do them every time, like really often. But what these experiments do show is that the channel efficiency changes throughout time. So maybe, and this is natural, like maybe at one point in time, you spend $100 on Facebook ads, and this $100 converted into one person. that went in and bought whatever products you wanted and then continued to purchase through the website or your business. And maybe some time later, you had to spend double to get the same level of conversions. So what happened in the middle? You don't really know. So this sort of temporal dynamics of the efficiency of the channels wasn't being accounted for by any of the traditional models of media mix that we had seen before. And this was really difficult to try to work with. So we've developed a way using Gaussian processes to try to learn how the efficiency of the channels changes throughout time. So we still assume sort of the same simple marketing channel effects, these sort of saturation effects, the carryover of spending on 1 week will affect the future weeks in some decaying way. But now also these parameters of efficiency change throughout time in a way. And so that gave us the ability to have this sort of temporal flexible model. And we started to try to experiment with this to see what we could gain as insights from it. So one of the key things that was nice was that with Gaussian processes, you can incorporate many types of properties into the function that you're trying to learn. So what we did was incorporate seasonality and also linear trends. So that's something that the marketers actually wanted. They wanted to see, we know that maybe in Christmas every year, there's something special that happens to our brand. And so people flow in and do something. And so they wanted to see how the efficiency of the channel was being modulated through the seasons. And maybe there's some linear trend to this. And so we've developed a way using different kernels to incorporate these sort of piecewise linear trends and seasonality effects that the marketing team wanted to see. And then the other thing that was difficult and actually nice to do was that, again, with just not having the Gaussian process, the model was hard to identify, and you could have some channels be imputed to be super efficient, but then maybe they weren't, and there was quite an uncertain spectrum of this. Adding Gaussian processes that could vary through everything and potentially vary across channels made the problem of unidentifiability just worse. So the way in which we dealt with this was adding a hierarchical structure to the Gaussian processes. So essentially, we allowed every channel to have its own sort of channel efficiency, but they should all contract to some global average across channels. And so this sort of concerted pattern allowed the channels to show what was being seen in the lift test, which was that channels efficiency changed throughout time, and also captured seasonality patterns that you saw in conversions. So it was a really nice project in the end afterwards, after having seen everything that we could do with this sort of simple a priori model and then extending with GPs.
Yeah. Each time I was looking at this model, I was amazed by the beauty of it. And it does sound complicated, but once you start thinking about it in building blocks and understanding what each building block is doing, I find it not that hard. Actually, it's like each block has its purpose and is there for a reason, and not just for like the sake of complexity or beauty or things like that. It was really like, as you were saying, the GP's building blocks are really awesome, and that's really something. That's also why I love GPs, right? It's like they are incredibly powerful, and yet they are still somewhat easy to use compared to theoretical processes, for instance. And you have that cool interpretation of the parameters of what the GP is inferring, as you were saying, and you can like customize them almost as you want, and adding terms, removing terms, and understanding how those terms relate to the problem at hand. And then you can add the hierarchy on top of that, which is really, really, really cool. And that way you infer a time series, but also regularize it towards a common trend across marketing channels. And that was really something that blew my mind. I was like, oh, that is really, really awesome. And also on that project, we used a lot the zero-sum normal right, constraint. So which is like constraining, for instance, the effect at each time point, if I remember correctly, the effect of each channel to sum to 0 or something like that.
Yeah, yes. So we still have to finish through part of the math of this, because at least for that case, we have everything sorted out. Zero-sum normal is just some sort of reparameterization of a classical hierarchical model with Gaussians, where you say that you have some population parameter, like for instance, the mean of a normal, and you then have many members of this population, and you assume that the members are exchangeable between each other, and you try to infer through this sort of hierarchy what's the mean of each of the members, and at the same time what's the population mean. So you can basically rewrite this into saying, instead of working with the population mean, you work with, and there's only 10 individuals, for instance, and you have a limited number of individuals that were actually observed. You can reparameterize this to say, I want to look at, not learn the population mean and the 10 individuals means, but I want to infer one parameter less. I just want to look at how much these member means deviate from the sample mean. And so with this, you manage to fix and remove one identifiability constraint. So something that relates the sample mean and the population mean of this hierarchical distribution. You can rewrite this and get something that can be written in terms of a normal plus something called a zero-sum normal, which is a multivariate normal distribution that's basically forced to have zero covariance on one particular direction of the covariance matrix. And this direction is the one that has, it would be the vector of everything being equal to 1, every element equal to 1, which represents where, the direction that encodes the mean of these. So I know that, I'm sorry that I went into something that was technical math, but it's hard to explain.
Yeah, that's good. From time to time, you need that. That's perfect. And we use that, and that's something that normally will make its way into the version 4 of PyMC, so that zero-sum normal distribution, which is something you have been working on, actually. So adapting that to V4, the PR will make its way to the main package
eventually.
One day, hopefully in the near future, but that's open source. Actually, I'm down to help you working on that, Luciano. We should team up and get that PR done. I can help you with the stuff you don't like.
The stuff that I do like, that I haven't finished on that, but which eventually will, is if you try to do this sort of zero-sum constraint on a multivariate normal, and you have different covariances for each member, different variance for each member, then I figure out how to write the log likelihood of the distribution for a case where you have just one axis that has to sum to 0, but if you have more than one axis, then figuring out the math to get the log likelihood computation. I still haven't worked my way through that linear algebra stuff, but eventually I will. And once we do, we'll have the zero-sum normal in, and we then have to also we also need to write something that tells you how to reparameterize your models, if you want, from the standard hierarchical way into something that has this zero-sum normal and still say these two models induce the same posterior distribution, which is the case for some special way of parameterizing.
Yeah, indeed. So yeah, we should team up for that PR. And yeah, so that was the cool thing. And then also the GP, the Gaussian processes were actually parameterized in a more efficient way with some algebraic tricks of decomposition, basically, of the Gaussian processes in eigenvalues and eigenvectors. These were developed in V4 too, and also I think at the end of the project, Bill Engels, who is the GP guy of PyMC, I think he added or he's still working on that, but started at least working on adding the GP API, that decomposition to the GP API, right, of the package?
It's in PyMC experimental.
Okay, perfect.
I think that PR hasn't been merged yet, but it should. The thing that was missing were doc strings.
Okay.
So yeah, I also contributed to that. So the nice thing is that you can write a Gaussian process instead of having it in terms of the normal way in which you do it with the multivariate normal, you can write it as something called a spectral decomposition, which uses some special theorem to do the spectral decomposition. And the key thing is that then you can cleverly pick how many eigenvectors you want. And this reduces the dimension of the problem of how many random values you want to infer in your model. And that really speeds up the model.
Yeah, that makes the model way faster. And so, yeah, I put a link to the PyMC experimental repo in the show notes so that people who are interested can check out that PR at docstring if you want. And that way you will have contributed to that PR. So if you're interested in that, feel free to reach out to me, to Luciano, or to anyone on the GitHub repo. I am sure that your contribution will be really welcome. So this PR is just added to the show notes. Thanks, Luciano. And yeah, so basically this decomposition of the GPs, which make it much faster to sample. This is what you did for that project. And then Bill is adding that to the PyMC GP API. And also, there was some out-of-sample predictions that needed to be done because of there's some normal and the GPs. So, so many things and developments happening from this work on media mix model through PyMC Labs. That was such a huge project and fascinating. We just scratched the surface here, but I also put a link to the blog post. For now, there are 2, but the third one is in construction. So 2 blog posts that Ben Vincent, a member of the Labs team, wrote about that work that we did for HelloFresh about the media mix model. And also I will interview Ben very quickly on the PyMC Labs YouTube channel to go through basically those blog posts, and let's go kind of have a read of the blog post with author's comment if you want. So that's the director's cut of the blog post. So we'll do that very soon on the Labs channel. So I will put a link also on the YouTube Lab channels in the show notes of this episode, so that if you're interested, you can subscribe and be the first to know when those videos are released. It's going to be the next video. So time is flying by, and you already gave me a lot of your time, Luciano. So thanks a lot. Something I want to ask you, though, very fast before the last 2 questions is, we just talk about that basically Bayesian marketing. And so I'm wondering if you have an idea of what the future of Bayesian stats in marketing would look like to you, especially things that could be improved.
So I think that the marketers, what they want to see also is they have media channels that affect what they call the journey of a customer. So they imagine the way in which they conceptualize this is that there's a funnel through which people go through up until they decide to purchase or become involved and then eventually churn out of the company. So one is just becoming aware of the existence of the company. So this is something really high level. Then they go down through the purchasing funnel into something that's more directed. They go inside of the website, or they go inside of the store. Then they select an item or select the product by the brand. Then they maybe contact the company. Maybe they pull out a request, or maybe they just go and buy. So all of this journey that goes through different, you could think of levels in this consumer funnel perspective, is something that they're really interested in. So they want to know if an advertisement is contributed to which part of the funnel of the consumer's journey. And with the media mix models that we have at the moment, this funnel idea is not included at all. So something that they do want, and they do try to measure with some sort of interventions, are these customer journeys. And to optimize your media spend, eventually you have to incorporate all of the information. You just know that maybe there's some ads, or maybe there's some channels that don't contribute to making the conversion, but just give brand awareness. And this brand awareness maybe brings more flow, more natural flow into other advertisement channels that are more targeted, and then contribute to lower levels of the funnel and then to the purchase. So this, I think, is called multi-touch attribution. So these sorts of things, I think, are needs from people from marketing, and it would be great to eventually work on models with Bayes to try to address like the full scope of all of this.
Yeah, so it's like more things that touch more on basically causal inference, causal attribution of events.
Yeah, like all of this is causal inference. Like they want to see, they paid some money for an ad on a website and they want to see, what's the return of this investment? How much of this money went into the money that I then gained through conversions? So they always kind of want to do these causal claims. And the problem is that you don't really have these counterfactuals, and doing causal inference is so hard. So yeah, I think that the future will be really tied to progress in causal inference methods and maybe trying to model more of the full journey of consumers.
Yeah, cool. Well, exciting times ahead, especially if we can still use hierarchical Gaussian processes with that.
Most certainly will be able to.
Perfect. So Luciano, I think it's time to call it a show. I mean, I had so many questions for you and I only went through just a few of those, and even the questions I asked you, I could have had in more deeper questions to go deeper into the topics, but that's life. So before I let you go though, I'll ask you the two final questions I ask everyone at the end of the show. So the first one is, if you had unlimited time and resources, which problem would you try to solve?
Oh, that's so hard. So I still like neuroscience, so I would maybe be going into learning stuff, if modeling the brain, dynamics, neurons, things like that. So maybe that, but it's something that I don't really know yet which problem. As you've seen, I've changed a lot of topics throughout the time, throughout my life. And I've found it pleasing to work on many different things. And so I'm happy where I am at the moment. Maybe if I had more time and resources, I would spend it working more on open source, which is something that I love to do.
Yeah, I understand. And second question, if you could have dinner with a great scientific mind, dead, alive, or fictional, who would it be?
That was so difficult. I thought I would have come up with an answer by now, but I honestly don't. So I think that from my physics background, I think that a person that has always sparked curiosity for me has been Richard Feynman, who seemed to be such a strange and interesting person. So I think that I would love to meet him. But then again, like, I'm not so involved with physics. So yeah, what would I talk about? Maybe bongos. I don't know. But yeah, I think that Feynman would be a really interesting guy to talk with.
Yeah, for sure. And for what it's worth, some past guests have answered Feynman too. So that dinner table is getting packed by the minute. And by the way, I think Thomas Vicky answered Richard Feynman too to that question.
Awesome.
So are you sure you don't want to change your answer? Because otherwise you will have to have dinner with Thomas.
Oh no, that's awful.
Yeah, I think you should change your answer. No, of course not, Thomas. We love you. Okay, Luciano, muchas gracias. That was really, really awesome. So many topics that we touched on. And again, I really love the randomness and the sinuousness of your path. That's really inspiring, and that also makes me feel less alone in that sinuous path world. So, as usual, I put resources and a link to your website in the show notes for those who want to dig deeper. Thank you again, Luciano, for taking the time and being on this show.
Thank you, Alex, for having me.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.